And so I'm required to, well, I have to find these out. Can somebody take a look at the camera there and see if it's in focus? Because right now it's completely out of focus. Just for a second, as long as when I'm in frame it's in focus. Let's see if it picks this up.
Yeah,
Okay, good.
that works.
All right, great.
You have to write pretty big though.
Pretty big for it to see it?
Like that size is.
Well, on that tiny screen.
Yeah, no, but I know. I'm just saying like, oh no, now you're not.
No?
Now you're not in focus.
Oh boy. Okay, hopefully as I write things it'll be okay.
Where's your focus button?
I don't think there is one. I think it's all auto.
Oh,
Is
Okay.
it going in and out?
yeah,
Can you zoom out a little bit?
yeah.
Thanks. So the other reason I'm recording this is because I need to apply for a job. And I've been requested to record a 10-minute segment that showcases teaching. But I'm a mechanical engineer, by the way. Do you guys know that? I'm not a programmer. You could probably figure out that I'm not a programmer because I don't remember anything. But I'm actually a mechanical engineer.
Do you want me to stop this and start it?
No, that's fine.
Okay.
I'll cut it. I'll have to cut it at some point. But yeah, as long as does it look better when it's out further up? Okay. So I'm applying to mechanical engineering departments. I don't think that the computer programming stuff that we learn in class is maybe the most appropriate to send to them. But I do think that some of the math is more general. It transcends the particular application. So I thought today would be a good thing to record, and I'll pick whatever 10 minutes I do well on. The rest of it's going to be crap. We'll see. Hopefully I'll hit some that is pretty good. Now, I had in my office, nicely, I had my whiteboard behind me in my office and a chalkboard in the other, and so that had all my notes. I was just going to be able to look over there and see what my notes were. So occasionally I'm going to have to look at this. Also, I've got some notes over there that I want to make sure. So today we're going to start off with, some amount of knowledge of math is going to have to be assumed. So some of the early material is going to have to be review. I'm not going to treat it from the get-go. But the first thing I want to talk about is functions. And you guys have seen functions before, right? We've got the concept of a variable, which you're all very familiar with from computer programming. But if we want to have a function, say, we write our function f of x, x being our independent variable, and let's say we've got the function x squared. And we like to represent that. This function, f of x, is the set of all points that, it's the function of all, it's all values that f takes on when x changes value, right? So if we've got x between 0, we should probably do the negative side here. Okay, -1, 1, etc. So we say we plug in x is equal to 0, and we see what the function is, right? So that's going to be the point 0, 0. X is 0, f of x is equal to 0. Does that make sense so far? And then we say x is equal to 1. And we plug it in. We say 1 squared is also 1. All right, so we go up here. We can plot a point. All right, this is the point 1, 1. And so there's actually a continuous curve. We can change the value of x. We get a corresponding value of f of x. And so we can plot f of x here against our x, and we end up with a parabola. Okay. I'm not going to cover functions in much more detail than that, but I can answer questions about functions if there's anything lingering in your mind. I think the functions are all pretty familiar to you guys. Does that make sense so far? Okay. Just making sure. We want to start from the beginning. All right. We can also have multivariable functions, just like you can have multiple inputs into your functions in Python. You can have multiple inputs into your functions in math. Okay, so we can have a function f of x1 and x2, right? Now how are we going to plot this on a whiteboard? Well, we could look at it a little bit differently. Instead of putting f of x on this axis, we'll have x2 on this axis. We'll have x1 on this axis. And really, this function we can visualize as some sort of shape that's coming out of the board, right? So I'm going to take, for example, the function x1 squared plus x2 squared. We'll try to represent that. So we take a value for x1, we take a value for x2, we plug them in. So let's start with 0, 0. We plug those in. Here we've got a value of 0. Okay. And then we've got, let's say, x1 squared plus x2 squared. Does anybody recognize what this function is looking like? Does it remind you of a shape you have seen before? This is a circle. This is the equation for a circle. Okay, and so it turns out that if x1 is 1 and x2 is 0, we're we're going to be right here, we're going to be 1 away, so the value of the function is going to be 1. And then x2 was 1 and x1 is 0, then we're going to be right here, and we're going to be, the value of the function is 1. Turns out that there's a set of points all around here, and for all of those points, the value is going to be 1. Okay, there's also another circle in here for that all the points are going to be a value of 0.5. So I'm not going to show you exactly why the shape is a circle, but you might remember that. And this is how we're going to visualize a function that happens to be a two-dimensional function, a function of 2 independent variables today. Right? And so we'll just draw, this is called like the level curves, right? All of the points on this circle have a function value of 1.5. All the points on this circle have a value of 1. And of course I could draw as many of these circles as I want, and they've each got a constant value on each of those circles, okay? So that's how we'll draw functions of multiple variables today in just 2 dimensions. It's easier if we could have a 3D picture, but we can't really do that, okay? Questions about functions? All right, then let's talk about equations, right? Equations. Oh, that sucks. Word doesn't erase very well. All right. Equations are when we say that we know that our function value is going to equal to something, but we don't know what x is. We know what our function is, but we don't know what value of x it should be in order to make it equal that thing. So we've got something like x squared minus 1, and we say that has to equal 0. Right? So our function, in this case, is x squared. And our equation is f of x is equal to 0. And the task is to solve for the value of x that satisfies this equation. And that's called solving for the zeros of the function, the roots of the function. Right? Seen that before. So in this case, we can solve it. I don't want to go through the process of how to solve it, but we can separate this, and we can say x plus 1 and x minus 1 is equal to 0. So this reveals there are 2 values that we can see that will cause this function to be equal to 0. X is equal to plus 1, x is equal to minus 1. So solutions are the values of x that cause this to equal 0. Now let's see, a few other things I want to note about equations. You can always write an equation. So let's say that I want to say, here's my function f of x, my x squared. And I say I want to solve the equation f of x is equal to b, right? So that really means that I want x squared is equal to b. But I'm going to tell you that I can always write these things, my same equation, in the form such that I want to solve g of x is equal to 0. How can I take this and write it in the form such that when I solve this, I really solve this? When I solve for this x, you need to tell me what g is, such that if I solve for the x here, then that's going to be the x that satisfies this one here. All you have to do is rearrange this guy. How can I do that? Somebody raise their hand, let me know. Yeah?
X squared minus b.
Yeah, I can just rearrange this because I can subtract b from both sides. I can say x squared minus b is equal to 0. And if this is my g of x, then if I've solved for g of x is equal to 0, then I've really solved the same equation as up here. And this is really important because when we talk about solving equations with computers, we're going to want to write them in a very standard form. We're going to want to write them in the form always that we're actually only going to specify a function, and then and we're going to solve, the computer by default is always going to solve for when that function is equal to 0. All the routines that we're going to be using are going to solve for that function is equal to 0. So whatever function or equation we start with, we have to turn that into a function such that when that function is equal to 0, we've solved our equation. And you can always do this. It's always just a simple matter of rearranging by adding or subtracting terms to each side of the equation. Does that make sense? What questions do you have about that concept there? Okay, so That is the basics of equations. Let's talk about linear versus nonlinear equations. So a linear equation, well, actually, we should probably talk about equations of multiple variables, right? So we could have a function of x1 and x2, right? So let's say that's x1 squared plus x2 squared is equal to 1. That's a nice one. So you might recognize this from before, right? So what's the solution to that equation? What are the set of points of x1 and x2 that are going to cause that to be true? Yeah, as we visualize it again, we already drew this curve before. It's the circle here. That's it. This is a value of 1, this is a value of 1, and then all the points in between lie on a circle that is a radius 1 from the center, r equals 1. All right, so that's the solution to this equation here. But we can rewrite this like this. And if we solve that, then we've solved the same equation. All right, and so this is how we specify to the computer. So actually, for one of the first homework assignments, you wrote Newton's method. And that can solve, if you generalize your code, equations just like this. All right. All right, so let's talk about linear versus nonlinear. This is called a nonlinear equation because you don't just see, we've got our variables x1 and x2, and they're raised to the power of 2. There's something funny that's going on with them. They're not just alone, right? A linear one is going to look like a, which is a constant. This is not something we're solving for, times x1, plus b, also a constant, not something we're solving for, x2 is equal to 0, right? So our unknowns, which are x1 and x2 in this case, these are the only things that are unknown. These are just constant values, and we'll specify numbers for them. It's called a linear combination of our variables x1 and x2, right? So this is a linear equation, but when we start raising one of our independent variables to a power, or we take the log of it, or we take the sign, or we have some function applied to it, then it's no longer going to be a linear equation. Okay, so let's take an example. I'm going to write things in maybe a funny way. Maybe I'll say a x1 minus x2 plus, okay, let's say this is equal to 10c. Okay, can you tell me whether this is linear or not in x1 and x2? It's linear. None of these, but as soon as we add something like, times x1 squared here, or something like that, we could have an equation like this. Again, we can represent this. We can just change this to a minus sign and say this is equal to 0. Now we've gotten our standard form again. Right? But this is now a nonlinear because we've raised it to the power of 2, etc. Okay, so linear, nonlinear. Now, when you've got a linear an equation in 2 variables, 2 unknowns, but you've only got one equation, you've got maybe a family of solutions, right? There's a lot of points, x1 and x2, that all solve this thing. If we want to narrow things down to like 1 or 2 unique answers, just a few answers, a few different points that will solve it, we need multiple equations. Okay, so let's talk about multiple equations, linear and nonlinear. You guys can stop me at any time. This is going probably too slow for many of you, and especially if there are math people in here, you're going to think I'm an idiot. Because I don't teach math, right? And I'm just an engineer, and a lot of my math is intuitive understanding. I'm not very rigorous, so please understand it works for us engineers, and we appreciate you mathematicians who do the hard work in figuring all this stuff out to begin with, and we can just use it. And we often abuse it, but it works out for the most part. So, okay, so let's see, multiple equations. So let's take an example. I'll make something up on the spot. 10 times x1 plus 2x2 is equal to 5. So that is one equation, and so that's going to have more than one solution. Anybody know what it's gonna look like if we were to plot it on our x1 and x2 here? Yeah. Let's maybe pick easier coefficients so we can see this more easily. All right, that's what I'm gonna do. Yeah. Let's make this, I'm gonna make it really easy for myself, okay? So we can rearrange this and then we can see it very easily. This is the same equation because we can always rearrange it. x2 is equal to 5 minus 2x1. Does that make sense? I've rearranged it, so if this is x1 and x2, then we can say, well, when x1 is equal to 0, then x2 is equal to 5. What's that? Right there. So this is 5. And then for every increment in x, then we subtract 2 from x2. Sorry, for every increment in x1. So if x1 is 1, it's 5 minus 2 is 3. So we go over just 1, we come down by 2. We go over another 1, we come down. So we end up getting a straight line like this. Okay, so I just want to bring the geometry in the picture, because when we start doing, so all these points on the line satisfy this equation right here. When we start getting, because we're going to work today, by the way, where are we going? We're going to do solving linear equations, or seeing how we would provide the information to get an answer from the computer. How do we provide the information to solve a system of nonlinear equations? And then we're going to go to how do we optimize, how do we do nonlinear programming? And that's, I think, where we're going to end today. And nonlinear programming, even for the math people, I think is going to be new. So all this stuff is probably old news. You might see it from a slightly different perspective, but it's going to be mostly old news. But nonlinear programming is kind of the heart of it, and I think that that you'll find to be new. Okay, so we're working our way there. All right. So if we wanted to get a unique solution to this one, we're going to have to add another equation. So let's add another easy one. Let's add x1 plus x2, or how about minus x2? Make it even easier on myself. x2 minus x1 is equal to 1. Okay? So we can rearrange this guy here so that we can more easily see what line this is going to be. x2 is equal to 1 plus x1. Right? So when x1 is 0, the value of x2 is going to be 1. And every time we go up by 1 in x1, our x2 is also going to go up by 1. So we've got a line that's kind of like this. And we can find the intersection of these two lines, and this is the only point that lies on this line that's a solution to this equation, and it also lies on this line and is a solution to this equation. So we've got a unique solution to this system of two different linear equations. So some things to notice about these equations: all these linear equations, if they're just in two variables, they're nice to work with. You might have written them in the form y equals mx plus b before, right? Where y is our x2, x is our x1, m is the slope, it's this coefficient here. We say that every time we go over 1 in x, this is how far we go up in y, something like that. And this, plus b. And b is what's called, we usually call the y-intercept. It's when x is equal to 0, where is y going to be? So it's basically, it's called the y-intercept because it's where the line intersects with the y-axis. Okay. Is that stuff for you so far? Okay. Linear equations, systems of linear equations. I'm not going to tell you how to solve them, but I am going to say that sometimes when we solve systems of linear equations, and the math people will still be familiar with this, we're going to want to write them in a convenient notation of matrices instead of dealing with them in these kind of unwieldy form. It's a little bit harder to enter this into a computer than it will be to enter just the coefficients, just the numbers. We already know that the equation of linear, it has a special structure. And so we're going to respect that structure by writing it with matrices instead. So you might have seen something like this before. So actually what we're going to want to do is work with this actually in a slightly different form. So when we're working with nonlinear equations, we're always going to write them in the form some function is equal to 0. But for linear equations, we often want to write them in this form, ax is equal to b, actually. Yeah?
So since there are pretty much only two ways of solving it, like substitution or elimination, is there gonna be like a uniform way of solving it, or are we always?
We're actually not
do
gonna
like
talk about
either
how
or?
it solves it, and there's not just two ways, it turns out. Like,
Okay.
there's lots of very interesting, even iterative methods for solving it, where you guess a solution, you plug it in, and you get some sort of residual, and you play around with that, and then you keep on refining your guess. And it turns out for huge systems of millions of equations, that is gonna be a faster way of getting a very close approximation to any desired precision. And so that's gonna be different from anything you've seen before. We're not actually gonna talk about how that works, but it turns out there's multiple ways, yeah. But all we care about right now today is how we're gonna represent these things to the computer. That's probably the most important part, is kind of understanding a little bit of the geometry, what's going on, being able to visualize somewhat, at least in 2 dimensions, maybe 3, what's going on, but then also how to turn these equations, if you've got a problem like this, how do you turn it into a form that the computer is gonna be able to understand? And so in order to solve a system of equations like this into a form that the computer is gonna understand, we're gonna have to turn it into matrices. We somehow have to turn this problem here into ax equals b because it's linear. The computer knows how to solve this. And so the general way that you probably have seen before, I can remember at least in high school doing this, maybe even earlier, you could have seen this sort of thing. We can number our variables like we have here, right? And put them all in a line, and I want to write my equation such that all the variables line up in columns. So I'm going to write 2x1 plus 1 times x2 is equal to 5. And then this one I want to rearrange a little bit. This was nice because I could easily turn it into this. But I want to swap the places of these guys. So if I, now I can say basically this is a -1 on the x1. And this is a +1 on the x2 is equal to the one here. I can write this as a matrix, matrix times a vector. Technically, a vector is a mathematical object, and we're writing just the coefficients and basis. Mathematicians don't bother me about that. We're going to call it a vector today, and we write it like this, okay? So we take these coefficients out. We say 2 minus 1, 1, 1, times x1, x2, the vector, or the column matrix if you prefer, is equal to 5, 1. Who has not seen this sort of thing before? Please do tell me if you haven't. You've seen it before. You remember the rules of matrix multiplication. Okay, so we don't have to go over those. So this is equal to that. In that case, this is our matrix A. This is our matrix B. And we're solving for this vector x1, x2, or this list of numbers. And all we have to do in order to solve this on the computer, we're going to end up with something almost like, we're going to write something like solve A, B. And that is going to return this list of numbers that tells you the solution that solves it. It's going to give you the point, basically, that solves this linear system. Does that make sense? It's going to be as easy as that. Now, I want to say one thing while we're still on the topic, and it actually relates to what you were saying. Many of you, especially the mathematicians, and this is especially the mathematicians, are going to be a little bit surprised by this, because even a PhD mathematician that I work with was actually surprised to hear this, okay? So you might be familiar with saying that x is equal to a minus 1 times b. This is absolutely true, but it turns out that when you're working with numbers, this is not the best way to solve the equation. We're never going to, in this class, and if you ever are tempted to take the numerical inverse of a matrix for any reason in computation, there's another way. There's a better way, okay? We're never gonna, even if we have multiple right-hand sides, b, even if we're gonna have multiple b's and we wanna solve for the x that satisfies these different systems, it's never the best thing to take the numerical inverse. So this matrix sometimes is very poorly conditioned, they say. It's not very good. It's not a good thing to do. So we're never actually going to do that. We're always going to say solve AB. We're never going to say invert A and then multiply that by D. Okay? Yeah.
How is it poorly conditioned? Like what's
We're not going to talk about what that means, but in the process of finding this A inverse, you're going to end up having to do division by pivot elements in the matrix, if you remember Gaussian elimination, that sort of thing. Okay, so you end up doing division. When those numbers are close to 0, then you end up multiplying effectively a whole row of the equation by enormous quantities. And that becomes a problem. The better thing to do is you want to switch around your columns and you just massage the problem, basically relabel where the variables are in this matrix, and just shift around where they are, and you're just playing around with it, such that it's no longer going to be the same system that's solved by A inverse, but there's what's called a factorization, LU decomposition, that you can use.
Does it get to a solution that's close to the same?
It's exactly the same. It will give you the exact same solution. It's just going to look different.
Oh, okay.
Yeah, it's just going to be in a different order, basically.
Okay.
There's a different way of doing the operations that's going to be better conditioned. Okay. All right, but the point being, you want to solve a system like this, all you have to do is massage it into this form. And you're going to have a command that's like solve, and you're going to provide the matrix, and you're going to provide how we're going to provide the matrix, we'll get into when we start talking about NumPy. The notation for that, that's all just syntax, okay? It's basically a matrix is a list of lists, and you turn it into a matrix, an array object in NumPy, and we'll see how that works, okay? So that is solving systems of linear equations. Good. Let's do a nonlinear system. Okay. So let's think of an example of a nonlinear system. All right. So now maybe we have x squared minus 1 is equal to 2. That's a good one. And we'll do, I'm just keeping it nice and easy on myself. x2 minus 2 is equal to 1. That's no, I want, here, I'll put x on the other side. Let's say that this is our system. That should still be pretty easy, okay? I told you, so this is actually two equations, right? Let's visualize these for a second. Really this one, if we subtract, if we want to visualize it, we're going to turn it into one form. If we want to put it into something that the computer can solve, we'll put it into another form. Well, let's visualize this first, okay? So we can subtract 2 from both sides, and really we'll end up having x1 squared is, well, actually we can probably, we'll subtract, is equal to 3. That's what we'll have here. Is that the form that I wanted in? No, I don't want that. Well, that's a unique solution. That's not what I was going for here. I wanted x2 over here. Yeah, sorry. I'm thinking of, all right, let's pick a different equation. That's not what I wanted. All right, so now how can we visualize this? We can put x2 on the other side. And we can have x2 is equal to x1 squared minus 2. Does that make sense? Is that right? That's the same equation. No? No? Yeah. Okay, all right, so let's also massage this one into a form we can better see. We can see x2 is equal to x1 plus 2. All right, so if we want to visualize what this looks like, then we can put it on our coordinate system here, x1 and x2. And this guy you might recognize as a parabola. So a parabola, so if we plug in x1 is equal to 0, then we get minus 2. If we plug in 1, we get 1 squared minus 2 is negative 1. Okay. So we're going to end up with a parabola that looks something like this. All right. Okay, that's one of our equations. And then our other one is going to be x2 is equal to x1 plus 2. So our slope is going to be 1. Our y-intercept is going to be 2. So it's going to start up here. It's going to go up with a slope of 1. And so the solution is going to be somewhere around here. It turns out that this one has a unique solution. So let's say we wanted to solve with this with the computer. I said we have to put this in a form, g of x is equal to 0. where x could be x1, x2, a list of numbers. We can think of it, it could be multiple things. So really we want g of x1, x2 is equal to 0. So we need to just rearrange this just a little bit differently, okay? In order to solve this with a computer, we need to be able to turn this into x2, well, we can say x1 squared minus x2 minus 2 is equal to 0, and x2 minus 2 minus x1 is equal to 0. This is perfectly fine. We don't have to order anything in a special way in order to solve this one. Turns out that all we'll end up doing is basically we'll write a Python function. It'll look something like this. Def x1, x2, okay? And then we will form something like a list. Let's say we'll start out with an empty list, and we'll append to it something like, well, x1, and we'll square it. Minus x2, minus 2. And we'll do the same thing for the other one. We'll append another thing onto the end of this one, okay, that represents the second equation. And then we'll just basically return the list. And so we're taking in x1 and x2, and we're returning a list that is solved. That when these things are equal to 0, then we found the x1 and the x2 that we want. Does that make sense? It's not going to look exactly like this, but that's conceptually what we want to do. We're going to write a Python function. It's going to take in our values, x1 and x2. And that's how we're going to tell the computer, okay, whenever this returns a bunch of zeros, and only zeros, then we found the x1 and x2 that we're searching for. That's the point. Okay, so we've gone over solving systems of linear equations is one form. You find the A matrix, you find the B matrix or vector, and we're going to solve for that x. We're going to just have a solve function. For solving systems of nonlinear equations, basically we're just going to write a general function that takes in values of all of our x's and spits out all of our, the values of all of our functions. And they all have to be equal to 0 in our equation to be satisfied. Make sense so far? Yeah? All right, now that we'll get to the cool stuff. Let's talk about nonlinear programming. I'm going to skip over linear programming because it's just a special case of nonlinear programming. I'm really excited actually about linear programming this year in particular because, okay, linear and nonlinear programming are optimization. We've solved equations here, but an even more general problem maybe is, well, you can turn one into the other typically, but it's at least more general as far as computers handle it, is nonlinear programming is minimization. Find the values of our decision variables, x1, x2, etc., that minimize some function, but it can be subject to additional constraints. We've got to make sure that some equations are satisfied as well. Okay? So the linear version of it is when your objective, the thing you're trying to minimize, is linear, and all your constraints are linear as well. And fortunately, just released, SciPy 1.0 was just released like 3 days ago, and we're going to be using that, and that is a release, the first one where my linear programming solver is like the linear programming solver you can use in SciPy, because it's way better than it was before. There was an existing linear programming solver, and so this is just a, I get to toot my own horn for a little bit. I'm really happy with this. So you guys get to use some code that I actually wrote and is distributed, and other people are able to use now, so that's really cool. All right, nonlinear programming. The general problem, let's say, well, let's start with not the general problem first. We want to minimize, I'm going to start using the variable z because I want to avoid confusion. Okay. Find the value of z that minimizes some function of z. That's the minimization problem right here. So if our function of z is x squared, then let's just draw z, let's say that this is f of z.
You
guys
mean
can
z
show
squared?
me. What?
Z squared?
Z, that's right, yeah, thank you, good call, something like that. Now, this is z squared plus something, I don't know what this is exactly, this is not exactly that equation right there, so let's just say that this is my f of z. And you want to find the z that minimizes my f of z, right? And so you say, okay, this is the minimum. Make sense so far? Conceptually, this is what we're trying to do. Okay, let's think about a little bit more difficult one. Now I want to find the value of z that minimizes this guy here. Now, this brings up the problem that you run into with nonlinear programming. There's a difference between a local minimum and a global minimum, okay? This is the global minimum. This is the minimum that is lower than all of the other minima. But these are called local minima because they're smaller than any of the surrounding points. You look a little bit to the right and a little bit to the left, and all of those points to the right and to the left are going to have a higher function value. So these are local minima, but they're not global because there are many of them, and there's only one of them that can be lower than all the others. And math people don't talk about like sup and that sort of thing, supremum and all that stuff. I'm not good with that. So in engineering, there's no need to worry about that sort of thing. So we're going to say minimum. All right. Okay, so let's start looking at multiple dimensions on this same sort of problem. We'll also start handling constraints. Okay, actually let's start with adding constraints first. We'll stick with a one decision variable z. But in general, I could have multiple decision variables. They're called decision variables, z1, z2, z3, etc. We're always going to have a scalar function, so we're going to turn all these different variables into one function, and we still want to find the minimum scalar value of that function. That's the problem. But let's start adding constraints here, okay? Let's find the minimum of z such that, or subject to, we want to make sure that a is less than z is less than b. And so let's put in some values. Let's say that a is here and b is here. What value of z solves this problem? It's called a bound constraint. We need to make sure that whatever z, we want to find the minimum just in this section of the curve, right? So the value of z is the one here. Notice it's not the global minimum anymore. It's the local minimum that happens to lie within these constraints here. So this is called a bound constraint. This is one kind of constraint that we're going to end up seeing in our nonlinear programming. We're going to see different kinds of constraints. We're going to see linear constraints, and we're going to see nonlinear constraints as well. Okay, so let's start working with multiple dimensions, okay? So let's go back to our circle example. Let's say now we want to minimize over z1 and z2. This function of z1 and z2. Where we've got z1 minus 1 squared plus z2 minus 1 squared. And that's going to be the thing that we want to minimize. Okay, so what does this look like? Here's our z1, here's our z2. This is also a circle, or a series of circles, right? Each of these levels curves is a circle. It's going to be centered here, right? When z1 is equal to 1 and z2 is equal to 1, we're going to be right here, and this is going to have a value of 0. And at z1 is equal to 1 and z2 is equal to 0, we're going to have a value of 1. It turns out that there's, just a whole family of solutions, values that this curve can take on. As we get further and further away from this point, the radius of the circle tells us what the function is. Does that make sense? Okay. And so if I asked you to solve this one, what's the solution here? What's the solution to minimizing over z1 and z2 this objective?
That bottom part? 1, 0?
No, because we are trying to, okay, so remember, we're trying to minimize the function of Z1 and Z2.
Right, okay.
So where is the function value minimized? At one, at Z1 is 1?
No, it's like, it's like right up and right from the corner.
Actually, let's think, yeah. So I'm gonna label a few function values here. We said that at the point 1, 1,
Yeah.
the function of x1 is equal to 1, x2 is equal to 1, is gonna be just 0.
Right, yeah.
If we're at any of these, the function value is gonna be higher than that. If we're out here at a radius of 1, the function value is equal to 1. So where is the function minimized?
1.1.
Yeah, at 1, 1, right here in the center, it's got a value of 0, it can't get any lower to that. So that's gonna be the solution to this general nonlinear programming problem. In order to specify this to the computer, we're gonna write a function that takes in Z1 and Z2 and is gonna spit out whatever this number is. And the computer is gonna be able to look at that and tell us what values of Z1 and Z2 get the minimum. Okay? Now let's start talking about bound constraints. Let's start applying them to this problem. Let's say I want to modify this problem. I want to add the bounds that let's say 0 is less than or equal to x1 is less than or equal to 0.5. What does this mean graphically? How are we going to visualize that? We're going to say that we're not going to let this be a solution anymore, right? Basically, we're saying that we're only interested, this should be Z. We're only interested in Z1 and Z2 such that Z1 is between here and here. Can you guys tell me where is the solution to this problem now? So one way to think about it is like, you've got all these families of circles, and you want to find the circle with the smallest radius that has a point that's within this region. What is the solution to this guy here? Talk about it with somebody next to you for a second. What do you think? Is the problem making sense? Okay. We visualize this function as a bunch of circles, and the function value is the circle's radius. And we're trying to find the circle with the smallest radius, but we need to make sure that we find the value where it's the smallest radius, but we need to make sure that it's within this region.
Wasn't it 0.5?
Yeah, actually, it turns out. Yeah, I mean, it's, so where is the point? Show me where on here is the point that we're looking for.
Z1 half and Z2 half. No. Yeah.
Well, Z1 is 1/2 is right here, so that's good. The Z2 is 1/2 is gonna be
No, 1.
here. Yeah, it's right there. This is gonna be the solution here, because you can see that this is the circle with the smallest radius, and we're just barely kissing it with our bound constraint here. And if we were to, we could have other points here that are, further up or down on this curve or in this region, but there's only one of them that's on the circle with the smallest radius, 0.5, yeah. Okay, so that's kind of conceptually what's going on with this sort of problem. Then we can start adding different kinds of constraints. Now that we're visual, we've gotten 2 dimensions, we can start thinking about other kinds of constraints. We can add on constraints like Z1 plus Z2 is equal to 0.
Just a question, so
Okay.
is the solution here 1/2 or half 1?
Well, it's Z1 is equal to 0.5 and Z2 is equal to 1. That's how you can
That
think
is
of
the
it.
solution?
Yeah, that's gonna be the solution, yeah. Z1 is equal to 1/2, Z2 is equal to 1. That's gonna be the one, yeah.
I think I'm confused. How do you get the like first circle in the first place before you even like?
All these circles just come from visualizing what this cost function or objective function means. By the way, I'm going really fast, I know that. So this just maybe will tell you a little bit more about what we need to review, and we can review this stuff together, okay, in more detail, all right? What was the question again?
You know, it's like, I thought I got it.
You thought you understood it.
Yeah, but then like, once you talk about the box constraint, then I got
Okay.
confused what the
All right.
one before the box constraint.
Okay. These circles were just a way of visualizing this function. This is a three-dimensional thing. It's really coming out of the board. So instead of drawing like what this shape looks like in 3 dimensions, which is really hard, I'm basically just drawing lines where the value of the function is constant. So at these values of x1 and x2, the value of the function is always the same. It turns out that the value of the function is always equal to 0.5 on any of these points. So if we just want to minimize this function, no constraint, then it's easy. It's wherever it's 0. It doesn't get any lower than that. So you did understand that part, I'm pretty sure. Then we said we want to put on the constraint. We want to make sure, yeah, find a solution where you minimize this subject to the constraint that you can't violate this. 0 is less than z1 is less than or equal to 0.5. So we restrict our attention to the points in this region. We can only look at this area, okay? Points outside here, this is no longer the solution because it does not satisfy the constraint. But you can kind of see that there is a circle with the radius 0.5 that just barely touches that. And there's no circle with the smaller radius. Because if the circle had a smaller radius, like 0.4, then that circle is here. There's no points on that circle that go into our region. So basically we're trying to find, you know, the smallest level curve and where that intersects our constraint here. Does that sort of make sense?
So the point is like the center of the circle, or just a point in the circle?
It's just a point on a circle. It's just one way of looking at it. Another way of saying is like, let's test all the points, okay? Is this point here gonna have the minimum function value within this space? It's not. This is gonna have a function value of whatever this radius is. Is this point the minimum? No, because this is gonna have this radius, which is bigger even than that one. If you want to make this radius as small as possible, this function value as small as possible, then you're gonna basically choose the point that's on this line that's as close as possible to the center, and happens to be right there. So this is just trying to appeal to intuition. There are algorithms for once you have defined the problem, and by the way, we're gonna type into the computer a function that evaluates this, and we're gonna type these into bounds. We're basically gonna say with a special syntax that the lower bound on z1 is 0 and the upper bound on z1 is 0.5, and the computer will solve it for us. So we don't worry about how it gets solved. I'm just trying to appeal to your intuition for how to visualize the problem so far. And all I care about right now is just be able to visualize the problem, that's all. Yeah.
How would we use a second constraint? Because
Okay, so actually, if we had a second constraint right now, that's great. We've already narrowed it down to a single point. A second constraint is either going to be inconsistent and there's going to be no solution, or it's going to pass through that exact same point, right? Well, actually, that is absolutely incorrect. Let's add a constraint and see what happens, okay? So let's add this constraint here, all right? Let me redraw this a little bit cleaner.
Wait, so from just now, basically you had a circle, and then like, once you put the constraints on, the solution became a spot, like a point. Right.
The solution was always a point. We're going to choose one point that minimizes. In the beginning, it was at the very center, right? And then it became the point that was right, just kissing the bound. I'm just drawing all the points that have a certain function value, and then it's easier to judge which point is going to have the minimum function value and still satisfy the constraints. Sometimes you'll end up with multiple points that can still solve it, but in this case, there's always been only one. Yeah, yeah.
I was just saying the second one that you wrote down,
Yeah.
Z1 plus Z2 doesn't give us anything, so. With,
We'll see how to visualize that, okay?
Okay.
So we also want to satisfy this constraint now, okay? So let's draw this guy again. All right, so this is the 0.11. This has a function value of 0 right there. At 0.5, let's see. We've got a circle that's, sorry, this is a circle. This has a function value of 0.5, and then we'll have this circle, which has a function value of 1. Okay, so that's just visualizing our objective function. We want to find the Z1 and Z2 that minimize the function value. So without any constraints, it's going to be this one here. With just this constraint, we found it's going to be like this point right there. Now let's start saying, okay, so this constraint basically says we need to restrict our attention to the points that are in this region. We can't look over here. Now let's start, let's see what this one tells us. Well, this can be visualized as a line, right? This is just the line, we can rearrange it. Z2 is equal to -1 Z1 plus 0. Okay. So actually, wow, this is actually maybe a nasty line for us. It means that it's going to be this line, right? I should probably draw this with a different color. Okay. So actually, we're gonna have to start drawing larger curves here. Probably want, yeah, we'll start drawing bigger curves. Well, let's extend this first of all.
wait, we're not restricted to a unit circle? So we can use like any size circle?
Yeah, these circles are, again, just telling us what the
Well, you're just
objective
giving us
function
contour
value
lines to show us.
is. They're contour
Oh,
lines,
okay.
they're just showing, these are not constraints.
Okay.
We're not constrained to the unit circle, we're not constrained to any particular circle. We're
Right.
trying to find out, they're just used to visualize what the function value is, okay?
Okay.
We are constrained, we have to be, the Z1 has to be within these guys.
Mhm.
And Z1, Z2 have to actually lie along here, so we've further constrained ourselves. We have to be somewhere between here and there. Like, one of these, so the only solutions that are possible, the only things, here's the concept of feasibility. A point that satisfies these constraints is feasible. That's what we say is feasible. So all of these guys that are on this line are gonna be feasible points. We wanna find the one that minimizes the value of f. And so one way you could solve it is you keep on drawing circles of greater and greater radius until you find the circle that just barely touches this, right? Because if you draw a bigger circle and then it touches at more than one point, well, that's a bigger circle, that has a greater function value. You're gonna get some points. But I can probably guess that, well, let's see. I think that because of the way we've drawn this problem, the smallest circle is gonna be the one that just barely touches right here. Sorry, it's like kind of bad, but I'm gonna get, I think that this is the right point. This has become our solution in this case. Because we drew a bigger circle, well, then we'd start touching over here, right? And then, but this is gonna have a bigger circle, it's gonna have a bigger function value. So all these points were feasible, this is the one that has the minimum function value that satisfies all the constraints, okay? That's the idea for nonlinear programming. We have, in this case, a nonlinear objective function. I've shown you nonlinear constraints. This is actually a linear constraint, my bad. So this is a bound constraint. We write it in the form A is less than or equal to Z is less than or equal to B, with the understanding that Z could be Z1, Z2, and you have different A's and B's for each of them. And then you've got linear constraints. We typically write these in the form A times Z is equal to B. And I say these are equality constraints. So this is A equality, E is for equality, is times Z, all the Z's, right? Z1, Z2, Z3 in a vector is equal to B equality. We can also have linear inequality constraints. Okay, we could have A times Z is less than or equal to BI. Let's take a look at a constraint that we can visualize that's of that form, okay? Yeah?
How do you program this?
So we program it just by specifying to the nonlinear programming solver a function that evaluates this. We're gonna pass in the A's and the B's. We're gonna pass in the A matrix and the B matrix, and then in this case, we're gonna pass in a separate A matrix and a separate B matrix. All you have to do is specify these different matrices and write different functions, and it's gonna be able to solve it for you.
So
That's the
the
idea.
solver is already doing
The
something?
solver is already built in. Yeah, that's right.
What was the point of the E and I notation?
Okay, so the difference between these is, this one was an equality constraint. A
Right.
times Z is equal to B. This one is saying AI times Z has to be less than or equal to the BI's. So let's change this, right?
Right, but why not just write the inequality or equality symbol, like, and not put the I or E? Like, what
Because
is-
these are not necessarily the same matrix.
Oh, okay, I see what
Yeah,
you're
they
saying.
could have different coefficients.
Okay,
Yeah.
Where are those matrices? So they're like just a whole bunch of.
Yeah, these are, we could have lots of different constraints, right? In general, we're gonna have a problem that's got like maybe 100 dimensions, or 1,000, or 1,000,000 dimensions, 1,000,000 different variables, Z1, Z2, up to Z1 million. And so in order to, yeah, you could maybe minimize without any constraints, but sometimes real world problems are gonna have constraints. And so we're gonna have to apply those, and it can take the form of lots of different equations, and it's compact to write them in a matrix form when they're linear. Yeah. All right, let's look at an example with, let's forget about the equality linear constraint right now. Let's do a problem that has an inequality constraint, just so you can visualize what that looks like, okay? All right, so we want to get rid of this line here. And I'm also probably, I think I'll get rid of the, I'll just redraw this whole thing. So let's not worry about this bound constraint anymore, okay? Let's not worry about this equality constraint. No more equality constraint, we're gonna write up an inequality constraint, okay? Such that Z2 is plus Z. I want to write it this way. I want Z2 to be greater than or equal to Z1 plus 1. Okay? How can I rewrite this in the form? I'm going to tell you that to the computer, you're only going to be allowed to specify problems, constraints of this form. A inequality times Z is less than or equal to B. How can I turn this guy here so that it looks like something of this form? I've got a greater than sign here, right?
Z1 minus Z2 is less or equal to 1.
1 second, you said what?
Z1.
Z1 minus Z2, so we've subtracted minus Z2.
No, but that will leave it. It'll be Z2 minus Z1.
Well, it's gonna look like this is, and then there's a minus 1 over here, right? Because we bring the Z2 over there,
Yeah.
we bring the 1 over here.
And then it will
And
be.
so we've got, basically, we could write this as the A matrix could be 1 and -1. And our Z's are like Z1 and Z2. And this actually is less than or equal to -1. Yeah, I think that you've done it.
Would it be 1 though? Not -1?
When we brought this over to that side, because we kept this one positive, right?
Right.
Does that make sense? So this could be our A matrix, and this could be our B. Does that make sense? I think that we've,
No.
no?
Just bringing it over shouldn't affect the sign.
No, so we put this on the other side, so that this was Z1, this can be interpreted as Z1 minus Z2 is less than -1. Right? This says -1 is greater than Z1 minus Z2.
Okay, I got it.
Yeah. So another way that you can do it is you can rewrite it, and well, remember, keep in mind that when you multiply the entire equation by -1, you do get to reverse the sign. Okay, but the point being is we're going to have to maybe sometimes take linear inequality constraints like this, of this form, and we're gonna have to write them in the form where we are less than a b. And you can always do that by rearranging things, massaging them a little bit in order to get them in this form. So it's not very restrictive. The solver that you're gonna start working with is expecting the problem to be of this form. You might originally have your constraints expressed like this. You have to turn them into the matrices, and you might have to multiply certain rows by -1 in order to reverse the sign, the direction of this inequality. That's the idea. Does that make sense? Okay. All right, so that's linear inequality constraints. It's not so, do I need to draw a picture for this? We could draw a picture. What does this look like? Z2 is greater than Z1 plus 1. Let's just draw the picture of that. Let's forget about all the circles, right? Z2 is greater than. So the way I do this is I say, well, let's draw the line, Z1 plus 1, so the y-intercept is 1. And then it goes, it's linear, right? So we say Z2 is greater than that. So basically, any of this area is fair game. Actually, over here too is okay as well. All this stuff is all right. And then maybe our point, 1, 1. So I guess we can draw that. This is where f is equal to 0. That's excluded. We can't take that point, right? So we keep on drawing circles, and we find that there's a circle that just barely kisses it right there. And so I think that this is going to be our solution to this problem in this case. So adding constraints changes the solution. All right, almost there, almost there. Let's talk about nonlinear constraints. We can start having such that g of x, or z in this case, decision variables, is equal to 0. Okay, what's g in this case? We could take, let's take our favorite z2 minus z1 squared, yeah, is equal to 0. Yeah, that's what we want. So we can massage this a little bit. We see that this represents z2 is equal to z1 squared. So we could draw that as a parabola, right? So basically we've said that, well, we need to require that our solution is a point on the parabola okay? And then we can draw all of our level curves, right? This was the center for f is equal to 0. And then we had ones for 0.5, and we had one for 1, etc. So what's the solution to this one here? Well, we constrain that z2 minus z1 squared is equal to 0. What's the solution to this problem?
We have two solutions that kind of thing.
What's that?
0 and 1, 1.
Oh, no, I don't think that there's, I think there's only one. And I think you're correct that it's 1, 1.
Oh,
I think that this
it's
one
the
right
same,
here.
yeah.
It's 1, 1, z1 is equal to 1, z2 is equal to 1. They lie on this parabola, and they also are, it turns out to be the global minimum of the unconstrained problem in this case. That's right. Just by coincidence. Okay. We could also have, we could modify this a little bit, and we could say we want z, this has to be greater than, or less than or equal to 0. So what does this look like? We basically get z2 is less than or equal to z1 squared, right? And so that means z2 has to be less than or equal to z1 squared, then only the stuff underneath this parabola is allowed. Now, our solution is still going to be the same in this case. Okay, but I've introduced 5 types of constraints here. So our general nonlinear programming problem is that we want to minimize overall z, which could be z1, z2, all the way through, say, zn, right? We want to minimize some function of all those z's, z1, z2, all the way to zn. subject to the constraints, bound constraints, A is less than or equal to Z is less than or equal to B. So constraints on all the individual Z's, all the individual decision variables themselves. We are going to have possibly equality constraints, A matrix times Z is equal to B equality. And we specify that these are the equality because that could be different from the coefficients in the inequality constraints, is less than or equal to B inequality. We've got the G equality of Z is equal to 0, and we've got G inequality of Z is less than or equal to 0. Sometimes this is written as H and this is as G, just a different notation. But conceptually, we've seen examples of all these different kinds of constraints, and we see how these constraints are going to change the solution to the minimization problem. And the point being here is this is the general nonlinear programming problem, and there's a huge class of problems that fits into this form. You might have to massage things a little bit. Let's say you have a maximization problem. Find the maximum value of this function. Well, we can find the minimum of the negative of that function. So if we were to write, we want to minimize f1 of x, or excuse me, want to maximize it, well, we could just solve the problem where we minimize negative f1 of x. That's an example of the sort of thing that we might have to do. We already saw examples of where our inequality constraints, linear ones, were written in the other form. We had a greater than sign, right? But we just had to rearrange things a little bit, maybe multiply the entire equation by -1, and we can switch the direction of the sign. We saw that our constraints don't initially come in the form as equal to 0. We might have something on the right-hand side here, but we might have to subtract things from both sides of the equation, make sure everything is on the left, and then our equation is satisfied. We can write a function in Python such that when the outputs, the returns, are all 0, our equation is satisfied. Okay? All we have to do is specify the A and the B, the A matrix, the B matrix, and write functions for these and that. We put them into our nonlinear programming solver, and there is already a routine written for us that will get the solution. Okay, so now that you understand the concept of nonlinear programming, the types of problems it solves, let's look at a few kind of interesting problems. We'll turn those into figure out what the constraints are and what the objective function is, at least conceptually, and you'll be very well prepared for using Python's nonlinear programming capabilities in order to solve these sorts of problems, right? We start with a word problem. So all of this has been leading up to how do we turn a word problem basically into something of this form so that we can program Python to do it for us. Yeah. Okay. Yeah.
To clarify those 5 things, so the first one is like gets us between like 2 Z values, right?
Yep.
And then the second one is just like lying on a line.
Yep. Yeah, that's right. This is a linear equality constraint, and
And
it's like lying on a line or in multiple dimensions, a plane or a hyperplane. Yeah.
then the third one is like above or below.
Above or below a plane or a hyperplane. Yeah, we call it a linear inequality.
And then the fourth
Absolutely.
is
That's
like,
a great interpretation.
like on a like parabola, like
On some sort of manifold, some sort of, yeah, something where this is some sort of shape.
Okay.
It's lying on a surface in multiple dimensions,
And
sure.
the last one's like above or below.
Is like below or within or that sort of thing. Yeah, exactly. So this is non-linear equality. Yeah, this is great, actually. And nonlinear inequality is what they're called. And some examples, I suppose. Yeah, you gave the examples. These are simple bounds, right? We could block off regions of the space with lines, or planes actually, as it turns out. And then this one was, yeah, lying on a line. So on a line. And this one was like above or below a line. Or plane, hyperplane. And then this was on a manifold. On a, I'll just say shape. Manifold's the right term? Is that good? Good enough? No?
Technically, this is on or above or below too, because we have.
This is the equality.
No, the one before it.
The one before? Above or below?
Or on.
Or on, yeah, that's right, because it's inequality, exactly. Above, below, or on, one of the two. Above and on, or excuse me, above or on, or below or on, so one of those things, okay. And this one is on some sort of shape, and this is above or on, or below or on some sort of shape. Yeah, good. Or outside, within, that sort of thing, yeah. Great, thank you for that, a bit of interpretation.
And I think we're trying to minimize is like the value of FC.
That's right, and all this, these are the constraints, the things that have to be satisfied, but we still want to choose only the point within that satisfies these, that minimizes this function. That's right, and we showed a visualization of that before, but that was just a way of looking at what this looks like. Yeah. Good. Okay, so let's look at an example problem. The first one we'll start with, we're just going to do two, so I think this won't take more than half an hour more. All right. The first one is data fitting. Let's say you got a bunch of data. And you want to fit a curve to it. You've seen this sort of problem before, right? Let's say that we want to find the line that best represents this data. And you say, well, does that line represent the data very well? Well, first of all, let's think about the equation of the line, right? Y equals mx plus b. Is our line. What's wrong with this one? It looks like it's got the right slope, so m is right, or approximately so. But b is wrong, right? We need to shift this whole curve upwards a little bit. And then we could have, another line up here. Looks like the slope is wrong, maybe the height's right, etc. We want to find the m and the b for the line that's like, right through the middle here. That's kind of intuitively what we're trying to get. Right? That's the problem here. I have said that I'm looking for the line that best fits that data. Right? And these data are given to us. So the thing that we want to know is the m and the b. And the data is already given to us. So the data is like, x1, y1 is this point, and this is x2, y2, etc. So our job is to find the m and b. Now what is best? What do we mean by best in this case? There's a lot of different definitions. The classical definition for data fitting is that we are going to take a look at the distance, the vertical distance between the point and the line, and we're going to square it. And then we're going to look at the vertical distance here, and we're going to square that. We're going to look at this vertical distance, we're going to square that. We're going to sum them all up, and we want to minimize all that. So we've got an objective function right there. We want to find the line that minimizes the objective function that is all these differences squared, sum of the squares. Right? That's conceptually what we want to do. So we've got our function, our objective function. So we want to minimize this function of whatever we just described conceptually. Do we have any constraints? I can't actually think of any. I think this is an unconstrained problem because there's, maybe m could be, we could constrain it, but actually, first of all, what are the decision variables? What are our z1 and z2 in this case?
Just x.
M of base.
So x is, x1 and x2 are the data points that are given to us. We're not looking for the point or the place here we're not looking for a point in this space.
Oh, you're looking for like the best prediction.
We're looking for the best line. Yeah, what are you saying?
M of B.
M and B, exactly. So really our z1 is m and our z2 is b. Does that make sense? M and B are decision variables. We get to play around with those and find the values of m and b that give us the line that best fits according to this function. So really we've got a function of m and b. We'll say, we'll change this. So this will stay x. Okay, let's change this. This is z1 times x plus z2. Yeah. Cool. All right, so we want to minimize our function of our z here. And the function of z also has probably all of our x1 and y1, all of the points is part of this function. And so this function calculates the sum of all those squares, right? Now, do we have any constraints here? Do we have any bound constraints? Is the slope of a line somehow bounded? I guess it has to be less than infinity. It can be negative though, right? There's no fundamental constraints on what the slope of a line can be. And there's no fundamental constraints on what the y-intercept can be. So we probably don't have any. We actually don't have any linear or inequality, other constraints that I can think of. And it turns out that when you define the problem this way, if you define best fit as being the sum of squares, as we said, then this has an analytical solution. We don't have to rely on nonlinear programming. But we can start playing around with different objective functions with nonlinear programming. Nonlinear programming lets us say, like, what is the sum of the absolute values of all these distances? You can start playing with it in that way. And then you can start writing out that problem. Or we could constrain it. Let's say that for whatever reason, there were some additional constraints on our problem. That the slope had to be within a certain, we want to find a slope within a certain region, you know, the slope values, they can't be from negative infinity to positive infinity, or the y-intercept can't be all the way up to infinity. We could constrain those things, right? Conceptually, does it make sense how we can turn the problem of fitting a curve? What if we had a different curve? What if we want to fit a parabola to this, or you know, a second order, right? Instead of y equals that, we can say y is equal to ax squared plus bx plus c. What are our decision variables now?
ABC.
Yeah, a, b, and c are our decision variables, so we can turn this into really, yeah, z1, z2, and z3. Great. So we can do even more general things now with the nonlinear program. It fits very well into our framework. Okay, just by specifying the objective function accordingly. Now, writing out this objective function is actually pretty easy when you've got Python, right? Maybe it's difficult to write out mathematically, but I think you can write code that can evaluate it. And that's all you need to do is write that function and plug it in there. Okay. Last problem. Last example problem. And this is the most interesting of the lot because it actually is not going to look like this one initially. Okay? So back in 800 BC or so, Queen Dido of Carthage, she was bringing her people over from some other place. There was a dispute with her brother or something like that. And so they settled in this place and they talked to the person who owned the land there and said, I want to buy from you a plot of land and I'll give you this much money. Or maybe it's like, she said, all right, I want to buy as much land as I can enclose in a bull's hide. Okay, so if you take the hide of a bull and somehow enclose an area of land, and the guy was like, sure, I'll give it to you for like $15. And she's like, okay, well, I'm going to cut up the bull's hide into a long strip. So I've basically got a long string. And how do I enclose this land out of it? How do I enclose as much land as possible with a given strip of bull's hide? So the problem has become, let's say she's got, water over here. So all this is water. And we've got her bull's hide that looks like this. This bull's hide has a certain perimeter, or a certain length. Actually, let's call it L.
What do you mean enclosed? Just like cover?
So, yeah, anything, so not cover actually. She's gonna draw like with cones, you put cones at each of these places, and anything inside here, between here and the sea, is hers for that $15. So the problem becomes, find the shape of this curve that maximizes the area between the curve and the sea with a fixed length, L. How can we turn that into a nonlinear programming problem? So what are some problems with it? What is fundamentally different? Before I had decision variables, and now I've got, those were a discrete set, Z1, Z2, Z3, Z4, and I'm asking you to find what? Like the shape of this line. Can anybody think about how we might get around that problem? What's that? You said line integral? Yeah, you wanna think in terms of, higher math, but let's think actually in terms of the last problem. What did we do? We said we wanna find a curve of a certain kind. We said we wanna fit a line to this data. We wanna fit a parabola to this data. What did we do there? We didn't just say find a curve that fits this data best. We said fit either a line or fit a parabola. But here we want to find the best shape. Let's think approximately. Okay? Let's
I
say.
feel like it's gonna be like a quarter of a circle. I just
Yeah,
don't know
oh,
why.
she's just intuitively, and apparently Queen Dido thought the same thing. She made a quarter circle, or actually the problem was the C was on a line, and then there was a semicircle is what she found. Yeah, so the Carthage was founded like that. Okay, so that's the solution. You're absolutely correct. Circle, quarter circle is the shape that maximizes the area within it for a given perimeter. But we're trying to solve that with our nonlinear programming. Yeah.
Can we start from like first order and second order?
First order, second order. I like the idea. You say basically kind of choose an order in a sense, and like find the shape that's best for that, and pick which order is best.
For each order, we will find the line.
Yeah,
Of
that's
that order,
best,
yeah.
and then find the best one of those.
Yeah.
Well, let's go a little bit step further. Let's say I'm going to massage that a little bit. I'm going to give a proposal, and we'll see how we do this. Instead of thinking about a continuous curve that minimizes it, let's think about, I said actually cones before, and I think that was a good thing. Let's say, where are we going to put cones to mark off a boundary, and we'll connect all those cones with straight lines. So we've got a piecewise continuous curve here instead. And if we've got enough cones, then we can approximate any arbitrary curve pretty closely. Kind of like a polygon can approximate any sort of shape that you might come up with. What do my decision variables become?
The coefficients for each line,
Coefficient for each line, or
for this intercept.
each of these points. We've got x0, y0, x1, y1, x2, y2. If I say, all right, I'm gonna start out with 100 cones, 100 points, and I'm gonna assume that my shape is piecewise linear, it's gonna connect each of these points, then I can treat all these x0, y0, x1, y1 as our decision variables. We wanna find the decision variables are all these different values such that we can find the perimeter of this, right? Each one of these is just linear, right? So we can find the length of this line. That's just Pythagorean theorem, right? We can find the length of this line, etc. We can also evaluate the area, right? This is just a bunch of trapezoids. You guys seen the trapezoidal rule before? Maybe you remember that from early calculus. It doesn't matter. Well, we've got a rectangle here, and then we've got a little bit of a triangle here. So even if you don't remember the trapezoidal rule, that's kind of how it goes. So you've got a bunch of little trapezoids, which are like rectangles with triangles on top. So you can find all those areas. You can find all of this guy here, the perimeter, and you can make sure that it's equal to L. All we had to do is pick all the x's and the y's. These are our decision variables. So in this case, we've got z1 is equal to x1 or x naught, z2 is x1, etc. And then we've got z, I don't know, actually let's label them better. We'll make this y naught, etc. all the way until zn minus 1 is our last x, and then z n is equal to our last y. Okay, something like that. Let's massage this a little bit further. Okay, so actually on the assignment here, well, actually, we're going to leave it at that for now. Okay, but let's think about how we write this a little bit more carefully as our nonlinear programming problem. Okay, so these are going to be our decision variables, all the x's and the y's where we put our cones. And then let's take a look at the minimization problem. We want to minimize, and I just want to describe in words, over what decision variables? These are going to be all the x's and the y's, x naught, y naught, xn, yn. Ugh, I'm off by a factor of 2 here. N divided by 2. Does that make sense? This is replaced by z. Our function, what's the function that we want to minimize? Ooh, actually, wait a second. She wants to maximize the area, right? We want to minimize something. How can we do that? What's the thing? Negative. So we can say our f is going to replace by, well, what's the area? We want to negative of that. That makes sense. And then finally, what are our constraints?
The length.
The length here. So we want to find the length, given all those z's, you know, the zi, minus L is equal to 0. That's right. And so we can approximate the solution to what's considered to be the first problem in calculus of variations, which is more a kind of a generalization of calculus to where your functions are your variables. And this was one of the first problems, and they duped it out in the 17th century or 18th century, figuring out the formal solution to this problem. But we can throw like modern tools at it and get at least an approximate solution without knowing any of that math. And this is conceptually how we're going to do it. We're going to write a function that evaluates the area given all these points. We're going to write a function that evaluates the length of the line of the bull's hide given all those points. And we're just going to make sure that minus L is equal to 0. That's what our function is going to evaluate to. When that function is satisfied, when it's equal to 0, then we have found a feasible solution to the problem. And then the one that minimizes or minimizes the negative of the area is the one that maximizes the area and solves our problem. That's all I wanted to cover with today. So we've gone from, you know, basic functions. Did you see the progression here? We've gone from functions, we visualized those, we visualized equations and solution to equations, we visualized solutions to systems of linear equations as where lines intersect, or as planes might intersect in multiple dimensions. We've looked at solutions to systems of nonlinear equations as where curves would intersect, or shapes in space would intersect, etc. We talked about inequalities. Inequalities is like beyond those surfaces or inside. And we started looking at, you know, not just solutions to equations, but we want to minimize subject to certain constraints, which are basically like, we have to satisfy these equations or inequalities, but we want to find the point that minimizes this other function as well. And that's the general nonlinear programming problem. So we're going to see all this stuff coming up soon. We'll do another one of these sessions where we talk a little bit about calculus and a little bit about Fourier transform, because that's going to appear on one of your assignments. And so some of the odds and ends that didn't fit into this little lecture. Okay. Yeah. Yes, as well. Yeah. What other questions do you have?
What is the next lecture like? Just say.
I don't know. Yeah, we'll figure out a time.
Like Friday is good.
Okay. Well, maybe it can be at the same time too. Okay. Was this helpful? I mean, you can say that I need to prepare better ahead of time. That's okay. I should probably turn off the camera for this part. Yeah.